Welcome to Josh Does Math. Today we have a very introductory calculus problem that kind of hints at the idea of a derivative without actually telling you to find the derivative. So right here we're going to find the equation of the tangent to the parabola y equals x squared at multiple different points and with multiple constraints right here. So if we're going to look for the tangent to this parabola, we know that the tangent is going to have the same slope as the parabola at that specific point. And as you can see, our first point right here, our first point is -2, 4. So I'm just going to draw out the parabola quick so we can see what we're doing. So there's your coordinate plane, and the parabola will be just right up there like that. It's going to open upward. And we're looking at the slope at -2, 4. So that's going to be somewhere up here. Say -2 and 4. So we need to know what the slope is at that point, because that will be the same slope that this tangent line has along the entire line. So how do we find the slope at -2, 4? Well, we'll take the derivative of this parabola and evaluate the derivative at -2. So there's multiple ways to do this. I'm going to start with just assuming that you already know some derivative formulas, and we'll do it that way. So I'm looking for dx squared dx evaluated at -2. So first I'll just take the derivative. So if you know how to use this rule, this is a really simple problem. This rule is the power rule for derivatives. It says power out front, one smaller on the power. So you see how that exponent just got moved out to the front, and I made the exponent one smaller. So the exponent became 1, which of course you don't need to write. So this is the derivative of the parabola x squared. And now I'm going to evaluate this at -2. Okay, so I just do 2 times -2, and that gives me -4. So I know that the instantaneous rate of change right here for this tangent is -4. In other words, I can say that the slope is equal to -4. Therefore, whenever I go to write out this tangent, I have the slope, I have some x point, we'll call that x, and we'll say it's equal to -2, and I have some y point, that's 4. That's just this point up here that they give you in the problem. So now I can go and set up, I'll set up slope-intercept form using these numbers right here. So you know slope-intercept form is y equals mx plus b. And I have y, I have x, I have m. So basically we're just solving for b. So I'll put these numbers in. -2 plus b. This equals 8 plus b. I subtract 8 from each side. And then I end up getting b is equal to -4. Okay, so now I just go and set up slope-intercept once more, except I'm actually putting some values in. I'm putting in -4 for m, and I'm putting in this value I found for b, -4. So this is the equation for the tangent line to the graph. Just looking at the crude picture I drew, you can see, yeah, it does have a negative slope, -4, and the y-intercept is -4, and that looks about right. It crosses down here somewhere. So this is the answer to part A. So now we can look at part B. I'll do that below over here. I'm looking for the tangent to the parabola at the point where the slope is 8. In other words, they're telling me that the slope of the tangent is 8. Okay, and we know that slope is also the derivative evaluated at that point. So we know that dx squared over dx, which we already found over here is 2x, is equal to 8. Okay, Now, where is it equal to 8? Well, you just solve this equation for x. So from this, we know that x is equal to 4. You just divide by 2 on each side. Therefore, the information that they gave me up here is that the slope is 8, where x is equal to 4. Okay, so now I'm once again trying to find an equation right here in the form of y equals mx plus b. And I know that x is equal to 4. I know that m is equal to 8. Well, I need to figure out what b is equal to. And the only way I can do that is if I have y. So we got to pick out some y value, and it has to be the corresponding y value for this x value. So I'll just plug this x value in, and I get 4 squared, and that's equal to 16. So I know my y value is 16, so I'm going to plug in my y value, plug in my m value, plug in my x value, and I'm going to solve for b. So right here I get 16 is equal to 32 plus b, subtract 32 from each side, and end up getting negative 16 is equal to b. Now that we know what b is, we just write out the equation using m and b. And this is going to be the answer to part b. So we have part A on this side, part B on that side, and I'll do part C down here. So part C says, find the equation of the tangent to the parabola y equals x squared if the x-intercept of the tangent is 2. So right there with that bit of information, they're giving me a point on that tangent line. It's saying if the x-intercept of the tangent is 2, therefore the tangent goes through this point right here, 2, 0. That's a point that the tangent goes through. Okay. So with this problem, I'm going to set up the equation of the tangent and kind of move backwards from there and find the slope of the line afterwards. So it's going to be reverse order of what I've done so far. So I'm going to start with point slope form. Point slope form is y1 minus y2 is equal to m times x1 minus x2. And I'll say that the x2 and y2 are this point right here that I was given. So I'm just going to fill in those values right here. y1 minus 0 is equal to m times x1 minus 2. And if I just simplify this, you can see that this 0 over here doesn't really matter. And we get y1 is equal to m x1 minus x2. So this is the slope of the tangent. This is the equation for the tangent. And it involves the slope of the tangent right here, which we know is just the derivative at some point on this parabola. But we don't know where. However, we do know that m, the slope, is equal to 2x. And if we assume that y1 and x1 right here correspond to some point that's on the parabola, just like up here in the picture, you can imagine that even though they're not in the same spot, 2, 1 is down here. That's where it crosses the x-axis, and x1, y1 is going to be the point up here that's actually on the parabola. So if we assume that, then that would mean that 2x1, or 2x, we can call 2x1, because that's going to be the slope evaluated at x1. Okay, so now I'm just going to distribute on this right side here. So y1 is equal to 2x1 squared minus 4x1. And because our curve that we're given is y is equal to x, I can say that y1 over here is equal to x1 squared. So now I'm just going to solve for x1, because then I'll know what this x value is that results in this point wherever it is on the curve. Okay. So I'm going to subtract, I have negative x1 squared is equal to negative 4x1. Divide by negative x on each side, and I get x1 is equal to 4. So that's the value at which this derivative is evaluated to give us our m value. Okay, so now right here I have the equation of the line. So now I'm just going to fill that in with what my x value is. Rather, I'm going to fill this in. I'm going to fill this equation up here with my m value. So I'm going to make it more generic by using y and x instead of y1 and x1. So now this can apply to any point on the curve rather than specifically y1 and x1. So I'm going to say y is equal to mx minus 2. But I know that this m value uses this x value. I know that m uses the x value up here at which m was evaluated. I know that m is 2x, so this is going to be 2x1. And I know that x1 is just 4. So y equals 8, x minus 2. And if I distribute that, I get y equals 8x minus 16. So that's the equation of this tangent. You can see it's actually the same equation as we had for part B. Now let's say that this whole time you didn't know how to do the power rule up here. You didn't know how to do this power rule. One smaller on the power, you pull the power out front. If you didn't know how to do that, and let's say instead you were using the limit definition of a derivative, could you still figure out this derivative? Let's see. So we're looking for dx squared over dx. And we know that a derivative is defined as the limit of the function value plus some h minus the function value all over the difference between those 2 points, which is going to be h. And you're taking the limit as h goes to 0, as h gets infinitely thin. And that will give you the rate of change at that point, f of x. So we're going to use this definition of a derivative up here and see if we can use that to figure out dx squared over dx. Okay, so I know that my function value is x squared. So I'm taking the limit as h approaches 0 of x plus h squared. It's all inside the parentheses here, because for every x I'm plugging in x plus h. That's what this says to do up here. So for every x I plugged in x plus h minus, and I'm just going to have the function value at x. Okay, now I'm dividing by h, so I put h down there. Okay, so to simplify this, I'm going to use FOIL up here. So that's going to equal limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared over h. And the reason I had to do FOIL up here is because you can see if I were to just try to evaluate this limit with direct substitution, I'm going to get something on the top here, and I'm going to get 0 on the denominator. It's actually, if you plug in 0 for each h, you're going to get x squared minus x squared. That's 0 all over 0. And 0 over 0 is an indeterminate form. So to avoid that and work around it and cancel some stuff, I'm going to use FOIL to distribute this. So I get this foiled monstrosity in the numerator. Okay, now as you can see, this simplifies down to limit as h approaches 0 on. Right here, this cancels with this. And so I'm left with this. 2xh plus h squared all over h. As you can see, a factor of h can cancel. Oops. Limit as h approaches 0 on 2x plus h. Now I can do direct substitution, and what do I get? 2x. So that's my derivative. So that's just another way of doing what we did up here using the power rule for derivatives. If you don't know how to do the power rule, you could have done it this way and gotten the same thing. But there we go. That's that problem done.